Hello, I'm Ian McCullough, and this is a short lecture on building empirical distribution functions in Excel. Now, histograms make intuitive sense to most people. They kind of show you where the data occurs. So if you look on the histogram here to the left, you see that, hey, there's a sharp point there in the center, and then it kind of fades off, kind of like a little bell curve, if you will. But if you look at the distribution on the right, it looks a little bit different in shape. And there's the same number of data points. In fact, this is showing the same data. The difference is the width of the bins. If you look at the right, the width of the bin in which we accumulate a number is wider than the one on the left. And so what I've done is I've just stacked the data points kind of on top of each other so you get an idea of where they fall. And what you can see is your decision on how wide you want to make that bin can alter the shape of the data, which can affect your determination as to what the distribution is. And of course, if you shift where the bin begins and ends, that will also have an impact as well. And so for this reason, we don't want to use histograms to represent data. We want to use an empirical distribution function. An empirical distribution is to a cumulative distribution function as a histogram is to the probability density function. So just a quick review, the bell curve that you see in the upper left, that is a density function. So it's basically describing the frequency of how often data occurs at that value. And so there's no way to say, hey, what's the probability at an exact point? It's a range of values. So here this is showing what's the probability the value z falls between -1 and 0. Now, if we integrate that area under the curve, then what that does is it gives us a value on a cumulative distribution function, and so we can actually read probability. So here, if you were to look at when z is 0 and read that value on the CDF, which is 0.5, that would tell you the probability a number is less than 0.5, less than 0 is 0.5. If you were to do the same thing with -1, the probability there looks like 0.17, right? The probability that you'd be less than -1 is 0.17. And so if we want to actually understand what the probability is between -1 and 0, we would subtract that probability, that 0.17, from 0.5, and we would end up getting like a 0.33, or about a third third probability that an event would occur between -1 and 0. And that's the area of that shaded region in the PDF. So what we want to do when we're fitting data is we want to actually model that cumulative distribution function because it is not susceptible to error as a choice in how wide you make the bins. And if we can map out that cumulative distribution function, we can take the derivative of that to get the probability density function, which would then look like a histogram that we're interested in. Now I'm going to show you how to create an empirical distribution function in Excel. So the first thing we have to do is we have to create some data. So I'm just going to create a data column. And what I will do is I'm going to use the norm inverse command to generate some random data. And so the probability here is going to be a random number. And so I can just use the rand command. And I'm going to make this to be a mean of 10 and a standard deviation of 2. I mean, you can make whatever you like, right? But this is just for example purposes, right? And so now I'm going to take that data and I will just run that down and make 1,000 data points. Or maybe roughly. Okay, so what I'm going to do is, because that's a formula and it will change every time you update a cell, I'm going to copy that and I'm going to just put this in a new place here where I'm going to paste special, and I'm going to only put the values. So that now when I've pasted this, you'll see that they won't change very much, right? They won't change. So we know that the empirical distribution function is going to range from 0 to 1, right? Because a probability ranges from 0 to 1. So what we're going to do is we're going to first of all count how many data points that there are. So we'll just start with 1, 2, 3, and then I'm going to copy this pattern by highlighting the cells, and you'll see that it'll just number all the way till the end. I can do a Control Shift to the bottom, right? There's 1,000 data points, okay? So now what I'm going to do is I'm basically going to say that this will be the first data point divided by 1,000. And then this will be the second one divided by 1,000. And so what I'm ending up doing is I'm creating now a pattern that's going to increment these points all the way from 0 until the number 1. Okay? So what I've just done is I've now created the data point and I've created the probability. So now I'm going to take these values and I'm going to copy them, and I'm just going to move to a new sheet so that I have the data values. And actually what I want to do is I want to paste special again so that I only have the values, so that I've completely eliminated the formulas. Now, to be a purist, right, we need to select all of these, copy them, and then I need to replicate them, because what we want to do is we want to have 2 points per data point, and this is just going to be to avoid bias in the data. So you'll come here to the bottom, and I've now just copied the same values. We're now going to go back and we're going to resort the data based on the values. And so now you'll see that there is 2 data points for every data point. We've just doubled the data points. So the next step that we're going to do is we're going to take this probability, the x value, and we're going to shift it down 1 notch. And what is that doing? I'm getting rid of the 1, and I'm going back to the initial point, and I'm going to create a 0. And so what I have just done is, for this data point 3.4, there is a 0, and a line is now represented, it's moving up the y-axis to 0.001. And now that's the level it is, and now you can go over to 0.85, and it's still at 0.001, and then it goes up to the next level. So now that we have the data that we're going to be looking at, we next need to be able to make a model. And so in our model, we might make a model for the normal. We might make a model for the exponential. I might make a model for the gamma distribution. This is an example. And for each of these, we're going to have an error term that we're going to model. And to highlight these, I'm just going to choose different colors to represent each of these distributions so that we don't get confused a little bit later on. So for the normal, what we have to do is say, what would that value be? What's the probability of that value occurring or smaller, given that this is a normal distribution? So I have to put some parameters over here. And so for parameters, I know that the normal distribution has a mean and has a standard deviation. Standard deviation. I know that the exponential has a lambda value, and I know that the gamma has a mean and a standard deviation, I believe. So I don't really know what the mean and the standard deviation is for this. I guess I kind of do, but I'm just going to, let's just say it's a little different. Let's say I say that the mean is 8 and the standard deviation is 3. We know that that's not true, but that's just going to be my starting value. And lambda, I believe, is 1 over the mean. So let's just call that, it would be 1/10, but let's just call that 0.12, right, just to be off. And then for the mean, we can also use 8 and 3 here as well, which are incorrect values. But we'll use those anyway. These are just the parameters we're going to use. So for the normal distribution, what I would do is I would say equals norm dist for the normal distribution, and I'm going to put that x value, which is right here. And then for the mean, I'm going to go over here and select the parameter value for the mean. But notice I am going to fix those, so I'm going to add a character string, $, in front of the L and in front of the 3. And what that's going to mean is when I copy those cells later, they'll keep that same value. And for standard deviation, I'm going to do the same thing. And again, I'm going to put a string in front and another string symbol in front of that. And then for cumulative, we always select 1. Okay, so now when I select that down, it's creating what the probability is of that value or smaller occurring, right, given the normal distribution with these parameters here. So the next thing I have to do is I now have to calculate the squared error. And so that is going to be equal to, open a parenthesis, that's going to be whatever the normal value is minus whatever the observed value is from the probability, and I'm going to square that value. And now we will select that all the way down. Okay. For the exponential, we'll do something similar. We're going to now do exponent distribution, and we want that parameter, that value x, which is over here in my data. And then the lambda value is here. And again, I'm going to use the string to make sure that those stay consistent. And then I will make a 1 to make sure that it is cumulative. And then I will then estimate what the distribution is with the exponential. I will then, for error, do the same thing, where I will subtract what I calculated the error to be from the, or the y value to be from the exponential distribution, minus what we've observed, and then we square that value. Okay, and then last but not least, we'll do this for the gamma distribution. So gamma distribution, the value x is here, and I screwed up the parameters. It's alpha, beta, so I'll apologize for that, but I'm going to change this later. So this will be alpha, and we will make this string, and then for beta, string to fix the values, and then we'll also make that a 1. So I'll go back and change this to alpha and beta. And so now for my error is going to be this value minus this, and that is going to be squared. And so I can copy this all the way down, and I'll copy this all the way down. Okay, so at this point what I've done is I've now just modeled that the normal, exponential, and gamma distributions with these parameters here, and I've calculated the squared errors. So what I need to be able to calculate is the sum of squared errors. So the sum of squared errors for the mean, for the normal distribution is going to be the sum, open parentheses, of all the squared errors. So I will just Control Shift down arrow to capture all of those errors. Okay, and then for the exponential distribution, we'll do the same thing. So this will be the sum of the errors here. Control Shift down arrow. And then for the gamma, we will do equals sum, and we will Control Shift down arrow. And so now I have the sum of squared errors for each of these. Now, a little trick we can do is I'm going to say this is going to be the sum of all my squared errors. And this is now going to be an objective function that I am going to numerically optimize in order to fit these distributions to the data. So to get the solver function in Excel here, I have to go to Tools. Now that might be a little bit different. You might have to Google where the add-ins are for a PC. But I'm going to go to Excel add-ins, and I'm going to select the solver add-in. And so now you'll see that I have this solver function. So I'm going to position my cursor so that it's over the cell for objective function. I'm going to select solver, and it's going to basically confirm where is the objective function. So I'm going to put that here at cell P3. I want to minimize the squared errors, and I'm going to do that by changing the cells that are existing in this column here. And I can create constraints if I wish, but I think I'm just going to try and do this without any kind of unconstrained values to see what happens. And I'm going to hit solve. Now you'll see down here it's going to go through the trial solutions and it's going to try and minimize the values. And so what it's done is its solver results have basically gone through its little thing, and it has basically told me, hey, this is what we think the best objective function is. It can also ask me if I want to keep that solution or if I want to restore the original values. And I'm going to keep that solution. And so recall that the actual distribution was a mean of 10 and a standard deviation of 2. So we came pretty close to that in our estimate here. And this is for an exponential distribution, and then this was for the gamma. These sum of squared errors are telling you how much error is there. So we can see the sum of squared errors, what they are for each of the distributions. And so the distribution with the lowest error is the best fit for that distribution. So what you'll see here is that 0.07 is lower than 0.28, so the normal distribution is the best fit of the data. Now, if I were to change something, right? If I were to create a situation where I went to a different page and I created data that was, let's say, gamma inverse, okay? And I did that with a random probability. And let's say the alpha was 5 and the beta was 2. And I went ahead and copied this 1,000 times. And then I'm going to copy that, and I'm going to paste special, just the values. And then I'm going to copy that again, and I'm going to go to the bottom, and I'm going to double them. And then I'm going to take all of these data points and I'm just going to sort them. And so now I have the 1,000 data points doubled and sorted in that order. If I were to copy this column and go back to where I have my distribution and just drop that in, right? It then changes the the squared errors, and it adjusts the problem. So now I can use solver again to same objective function, same values from L3 to L9 that I'm going to do, and I'm going to solve those. Sets up the problem, and it's going to continue to iterate here. And I'm going to keep the solver equation. And now you'll see that the sum of squared errors for the gamma distribution is smaller than the sum of squared errors for the normal distribution, which matches our intuition. So this is essentially how you set up constructing an empirical distribution function to estimate the shape and the parameters of the distribution. Once you have those parameters, then it's fairly straightforward to simulate synthetic data. Thank you for your attention.